Mobile robots in shared spaces have to detect and track nearby humans. Existing human tracking algorithms typically fail when the subject is partially occluded or outside the field of view. Many robots are short, with sensors lying close to the ground, which can cause severe occlusions. Moreover, only part of the subject's legs may be visible, exhibiting a complex, highly variable appearance with irregular motion. In this work, we detect and track humans in these challenging conditions by means of a Kinect depth sensor using the TurtleBot as an example platform. First, 3D points farther away than 3.5 meters are discarded. The resulting point cloud is downsampled using a voxel grid filter. This optimizes computation times and leads to a homogeneous representation of near and far objects. The floor is found as the most prominent horizontal plane. All 3D points lying within 20 centimeters of the floor are clustered together, and clusters matching the approximate dimensions of feet are expanded upwards and retained as candidate legs. In fact, many such candidates are not legs. In order to distinguish legs from other objects, we use a binary SVM classifier. For a given candidate, the input of such classifier is the histogram of oriented gradients of the candidate's rectified depth image. The output is the probability that the candidate is a leg. Here, green represents a high leg probability, and red a low leg probability. The position of all candidates in each frame, along with their computed probability, are used as observations in order to track the individual legs, also accounting for the robot's odometry. Finally, people are tracked using a Kalman filter, considering that a person has two legs, but often one or both may be occluded or fused to a single detection. The system is currently implemented in MATLAB and processes 10 frames per second on a mid-level laptop. An optimized real-time implementation as a ROS node is in progress. The classifier was previously trained on a dataset comprising more than 2,200 frames shot in 8 different real-world environments. The system performs well even in difficult, crowded scenarios. Occluded subjects are often correctly detected, as well as partially visible subjects very close to the robot. RGB data is currently ignored in our algorithm, although we plan to use it in the future to improve the matching of legs belonging to the same person. When tracking multiple people at once, more sophisticated tracking algorithms could definitely improve our results, since targets often interact and occlude each other, yielding many missing and ambiguous measurements. We plan to use our system to enable efficient and safe robot motion in crowded environments.